Yes, I will talk about generic and type-level programming with Generics-sop, and just to get a rough idea, I would like to know who has an idea what data-type-generic programming is? Okay, great. Who has worked with generic deriving before, like with the built-in GHC deriving or generic deriving construct? Okay, that's quite a lot. And who has worked with scrap your boilerplate before? Okay. And who has, just to have a control group, who has not heard anything of any of these? Okay. Okay, great. So I will try to give you an introduction to what generic programming is all about, and I'll try to give you a couple of examples. And the basic idea of generic programming, or data type generic programming, to be more explicit, is actually this. You want to define usually an overloaded in the context of Haskell function that works for many different data types. And let's actually use monoids as a first example in this talk. Imagine you, monoids extend rather nicely over products, right? If you have a monoid structure on a bunch of data types, and you have a single constructor record-like data type, and every component of that data type happens to be an instance of monoid, then you can relatively easily define by hand an instance of monoid for that record type, simply by saying the empty, so the neutral element of the monoid is the neutral element in every component, and the binary operation is just sort of zipping the two records together where you apply the binary operation in every component. But if you would have to define that instance by hand, you still would have to write quite a bit of code, because it's a user-defined data type. It's not sort of a generic n-tuple, but it's a user-defined data type that you gave a constructor, and you defined the fields, and to actually define instance monoid of that thing, you have to write code. And so that's a typical example where you might want to use generic programming to have a way of sparing yourself this effort of writing all this down by hand. And rather than having to give an instance for all your thousands of different record types that you might have in your application and making them an instance of monoid manually, you would like to have one that works once and for all. By the way, if you have questions, then interrupt me immediately. Don't wait until the end. So, what we're going to do is, rather than trying to define our monoid operations for the data type that we are actually interested in, which is the A in there, the data type A directly, we're going to go over to a generic representation of that data type that I'm calling rep A. And I'm not going to say yet what that representation is, only that after applying this transformation, all data types in Haskell are suddenly going to look rather similar. And there is a common structure, and that common structure you can exploit for defining functions. And then, rather than defining, for example, the monoid append operation on A's as a function from A to A to A, we're going to try to define it for rep A's for any type A that is in this generic class. We're going to try to define an append operation that works on these representations and produces a representation again. And this is hopefully a simpler problem, because these representations, as I said, they have common structure, and you can work on them more easily. And then, once we have that, we can just use these transformations that we also have, the from and to function, to go back to the original data type, right? And then we can basically give an mappend operation that works for all types that are in this generic class. And then we have only the task left to make all our record types an instance of this generic class. But if the compiler can do this for us, or Template Haskell, or whatever, then we're done, right? Then we are more powerful as programmers than before, because rather than having to build instances for quite a number of different classes for quite a number of different data types manually. We just have to derive this one generic class, and then we can program in Haskell instances for other classes. Yes?
But does this mean that gem append becomes a not-total function and it can fail if you provide representations of two different structures?
No, because the representation, as you can already see there, is indexed by the type that it is a representation from. So it still guarantees that you're putting together two representations of the same type. Right? Okay, indeed, there are quite a few choices on how to define rep, and this is a simplified view that I've just given on the problem of generic programming. And if you'd ask other people, they would give you different definitions. But even if you take this definition and you look at all the plenty of approaches that are out there in just in the Haskell world alone to do something like generic programming, the most significant difference in style and flavor you get is by how exactly you choose your representation. And for example, the built-in representation that GHC uses, that I'm not going to talk about in this talk, is going to break everything down into essentially binary pairs and binary choices, like the either data type. So whenever you have a choice between two constructors in a data type, the GHC will generate something like an either for you, and whenever you have multiple fields in one constructor of a data type, GHC will generate something like a pair for you. And then suddenly, rather than having to deal with all the different data types, you only have to deal with binary choices and binary pairs, and that's it. But then the GHC representation makes it all more complicated again by doing other stuff as well. But that's one option. And we're going to look at a slightly different representation in this talk, which is implemented in this library that's called Generics-sop. So let's look at an example data type, this expression data type. It's just an abstract syntax for a simple language you have. It doesn't really matter. We're not going to use that data type very much throughout the talk, but here you have integer and Boolean literals, variables that are strings. You have an if-then-else statement that takes 3 expressions. So these are untyped expressions, right? I mean, you can build type incorrect terms. And you have an addition that takes 2 expressions and a greater or equals. So if we want to construct a value of type expression, what do I have to do first? What's the first thing I have to do if I want to construct any value of type expression that isn't undefined? Choose a constructor, right? I have to choose a constructor. How many choices do I have? 6 different choices because there are 6 constructors. Okay, let's assume I choose if, which is the 4th constructor, right? Then what do I have to do next?
Choose 3 more expressions.
Choose 3 more expressions, right? And if I had chosen the 5th constructor add, then I would have had to choose 2 more expressions. So I have to choose a constructor first, which essentially just boils down to choosing a number, right? I know how many constructors there are, and it's essentially just choosing a number in the right range. Like, I mean, we're usually starting to count from 0, so let's say from 0 to 5 here, right? And then depending on what number I choose, I have to choose values of a number of additional data types, and which ones depends on the choice I make, right? Okay. And that's really more or less the same for all Haskell data types. I mean, even sort of simpler cases, right? If I have this data type, list pair, okay, has just 1 constructor, still, I mean, if I want to construct a value of this data type, I have to first choose a constructor. In this case, that's simple. I choose the 1 constructor that's there, so it's choosing a number between 0 and 0. And then, depending on that choice, I have to still choose a list of integers and a list of Booleans, right? Okay. And if I consider this maybe data type that I've just, like, I wanted to have it in the code, not commented out, so that's why I've appended primes everywhere. It's just the same as the normal maybe data type. And that's parameterized, but that doesn't change anything, right? I mean, again, I have a choice between two constructors here, 0 or 1. And then if I choose the first, I have to do nothing further. If I choose the second, I have to pick one more field. So in general, I can say that whenever I have a data type constructed value in Haskell, it has the form that's roughly a constructor with a number attached to it, which is in the right range of numbers. And then it's followed by a, in general, heterogeneous list, because the different fields of the data types can have different types of the arguments of that constructor, right? So it's a number and a list, right? And that's essentially the representation that we are going to use in Generics-sop. So if I do from, which is the conversion function from the original data type to a generic representation on, for example, let's say on a Boolean literal true for my expression type, then what I get, can you read this or is it too small? Apart from the noise in the beginning, you get this SOP tag, which is just a new type constructor, but you get successor of 0, which is an encoding of 1, right? Because Boolean literal is the first, like 0, 1, like it has the number 1 of the constructors, right? And then, again, the I is just noise. It stands for identity. But you get a heterogeneous list where the cons operator is this colon star and the nil is the nil. And that has one element in it, which is the true, right? Okay. So that is the generic representation gives me something like a thing that looks like a number, and it gives me something that looks like a list, but it's a heterogeneous list. So let's do a different example. If I do from of nothing, right? Maybe had two constructors, nothing and just. Nothing is the first constructor, so it gets the number 0. And the first constructor has no arguments, so there is an empty list attached to it, right? Whereas if I do just of x, I get a constructor with a number 1 again. I get a 1-element list with x again. So now let's, as a final example, yes?
Why is there is no ambiguity when you do from nothing? Because nothing has type maybe A.
Right.
So the from has to be A to a rep A, and then you print that, so the A is ambiguous, right?
Yeah, so so the question is, why isn't that ambiguous if I don't know what the element type is? And that question is related to what I wanted to show you right now. So I'll hopefully answer your question together with the example that I'm just going to give. Let's see what happens if we choose, for example, the addition constructor for expressions, which is recursive, right? I mean, there are expressions back in there. And if I say from of add of, say, the numeric literal 3 and the variable foo, I get 5, which hopefully is right. Or is it 5? Or is it? No, it's 4. 4, yeah, but that's right. And then I get a 2-element list. But if you see the list contains actual expressions, right? So this encoding isn't recursive. You only really reveal the top layer structure, and if there is a new type in there, it's always the original type. And why is that related to your question? Well, because that means that you can give a generic definition for maybe of A completely independent of what A is. You don't need to require that you also have A as part of the generic class at that point. It really works because it's only one layer. It's never recursive. Okay? Yes?
What would be the result of colon T from nothing?
That's that's a good question. So we'll get there in a moment. Let's see. So actually, this is basically the next thing that I want to talk about. If you actually want to get these generic instances for the data types, then you have two options within the Generics-sop library. One is to use Template Haskell, and then you just write derive generic, and you get the generic instance for free. The other is to piggyback on the built-in derive generic mechanism that is already in GHC, but for a different representation, and then use type-level computation to translate the generation that GHC generates into the generation into the representation that we need here. Because this one looks a bit more simple, even though I'm not a huge fan of Template Haskell in general, but for this talk, I'm going to use the Template Haskell deriving mechanism. Okay, so the representation works as follows, and this is coming back to the from nothing type signature. We first determine a code of a data type, and the code is another type. And if you haven't seen that before, in Haskell these days, you can basically have arbitrary data structures on the type level, and so code is a type-level function that takes a data type-like expression and gives you a type-level list of lists of types. So if you ask for the kind of code, it is of kind star to list of star. So it turns a data type into a table, into a two-dimensional table of types. And the two-dimensional table of types just reflects the components of the data type. The outer list has as many elements as there are constructors, right? And the inner lists contain the fields of the constructors, right? So that's just the same. This is just the expression data type robbed of all its names, right? I mean, there are no longer the names of the constructors, and if you had any record selector field labels, they would also be removed. So it's only the bare minimum structure left. But apart from that, this is still the same. Okay, and then it's going to interpret the outer list of this code as a what's called an n-ary sum, and the constructors of this n-ary sum data type just look like piano naturals. So in order to make a choice between n elements, you have to select one. And you do that exactly by saying, I'm going to take the first, which is the 0 constructor, or I'm going not to take the first, which is the successor constructor. And then you still have to make a choice between the remaining ones. So that's what the sum structure is. And then the inner lists are going to be interpreted as heterogeneous lists, essentially, which are called n-ary products in this scenario. And then you have a structure which is essentially isomorphic to the original one, and you can convert back and forth with from and to. And SOP there stands for sum of products. And then it turns out that every one of these structures, sums of products, n-ary products, and n-ary sums, they're always, because it turns out to be very useful, and places are always parameterized by another type constructor, typically a functor, that wraps every element in there. And in this case, we're getting back a representation where the inner elements are just like applications of the identity, where we're going to see more. I'm going to show you a couple of examples first, and I'm going to look at because I mean, I want to show you, there's not all that much time in an hour. I want to show you some examples, and then we'll spend the remaining time looking a little bit more at how it all works. So let's actually start by writing something like a generic monoid definition for product types. And let's actually start by writing an empty thing first. And I'm going to give the definition, and then I'm going to walk you through it. So gempty will have the following type. It'll produce an A, right? Because the neutral element is just something. But what are the constraints? Well, A has to be in the generic class. And we'll have further constraints that in order to construct a value of a data type, you have to make one further constraint, namely that there is at least one constructor. Right? And in fact, we're going to be even more restrictive here because we only want to consider record types. There is no real sensible generic definition for monoid definition for data types with multiple constructors. So we're going to say we want to require that in order to use this MMT function, that the data type has only one constructor. Now we've seen that this code gives us a table, right? A two-dimensional table. And when does a data type have exactly one constructor? Well, that is if the outer list of that two-dimensional table has exactly one element. So we're going to say the code of A should be a single element list which contains some other type's access. Okay? And now we have to make one more constraint, because now, can we produce a neutral element for an arbitrary record type? No, because all the types that are in that constructor, they have to be an instance of monoid themselves, right? So for all these types access, which is a list of types, we have to require that they're an instance of monoid. Now, how do we write that down? We typically, we know how to write monoid of a particular type, but now we want to essentially require the monoid class for a whole list of types. And that's a construct that's also provided by the Generics-sop library, and it's called all. So you say all monoid of XS. And that just says for all the types in that list, we have to have an instance of the monoid class, right? This is the type signature of GMMT, and now we just have to write it. And how do we write it? We are going to write it top down. So we're going to start here, and now at this point we have a whole. This is unreadable, but it's not so bad. I mean, this is a thing of type A, right? And basically, since we are in the generic class and we want to produce something of the generic representation, the last thing we're going to apply is 2, right? Because well, now we no longer have to produce something of type A. We have to produce something of type sum of product of I of the code of A. And the code of A we know is a single constructor, reflects a single constructor data type. So in order to produce something of this SOP representation, we always need to, that's one of the more unfortunate things of the library, you always have to insert this additional new type constructor SOP. And then we have to make a choice for a constructor, right? But now we have required that there is only one constructor. So there is only one constructor we can choose, and that is 0, right? And now, what do we have left now? Now we have to produce, I can make that larger. Oh no, that is the wrong window. Now we have to produce an NP of I of XS. That's the type of that whole. So we have to produce an n-array product of all the types in there. But what do we know? We know that every type in there is an instance of the monoid class. So what we'd like to do is to just apply MMT recursively for all these types. And that is a bit, if you look, it's a bit like replicate on lists or repeat on lists. And who of you have seen the zip list applicative instance before? So if you consider the zip list applicative instance for lists, just treats lists as sort of vector operations, right? So whenever you have pure, you produce an infinite list actually of things. You use repeat, and whenever you use star, you basically point-wise zip 2 lists together with with function application. And we're going to use similar operations on heterogeneous lists. And so that's why the operation that we are going to use here is called HCPure, because it's slightly similar to the pure operation of a zip list. And we want to just use HCPure with mempty, and the rest is noise. So so we would like to ideally, oh, sorry. Okay. So ideally, we just like to write HCPure mempty. That would be perfect if we could do that. But unfortunately, we now have to help various things. I mean, one thing is that we have to wrap the mempty in an I, because ultimately everything is parameterized by a functor, and the representation we have to produce, every element, as you can see, also for the GHC generated ones, has to be prefixed with an identity application. So that's one thing. And the other thing is that HCPure, the C is for constraint, and that's the function that allows us to apply a function that is itself in a type class, like mempty, which has the monoid constraint. But unfortunately, GHC's type checker or type inferencer is not clever enough to figure out which constraint we actually mean. So even though the type signature here has all monoid, and even though mempty is in the monoid class, GHC is still not clever enough to line these two up. So we have to use a proxy argument, which has no other purpose except to tell GHC that we want to operate on the monoid class, right? And that's the only point. And that's it. That type checks. Okay. So let's see. Well, let's see if we can call gmempty on, what was it, a list pair. And that gives us an LP of empty list and empty list, right? The list pair was has one constructor, and it had a list of integers and a list of booleans, and it gives us an empty list and an empty list. And let's perhaps go and say, what is HCPure of proxy monoid of I am empty? And if we actually give the result type and say, we want an n-ary product of identity things of a, what was it here? It's a list of int and a list of bools. So that's essentially what we're doing, right? And that gives us two empty lists, right? That's the thing that happens in there. And if we had a data type that additionally was also looking for, I don't know, let's see, a first of int or something like that, then we would get the neutral element of the first monoid is nothing. So then we would get that generated as well, right? So this HCPure is really, it's taking the result type and basically driven by the result type we want. It's inserting as many calls as we need to that overloaded function and interpreting them in the right way. And then we're just injecting it into the first constructor and wrapping it in the SOP and transforming it back. All right? And this is a very representative example of what programming in generics SOP looks like, because that's the nice thing, let's say, as opposed to working with the built-in representation that GHC has, that by giving ourselves a relatively rich structure of these n-ary sums and n-ary products, the library can supply you with quite a number of really powerful higher order functions like HCPure and map-like functions and zip-like functions that you can really plug together nicely and write these things really as pipelines or function compositions of simpler functions. Whereas if you have ever seen a generic function definition in the And binary sums of product style as given by GHC itself, you usually just manually write out lots of different type class instances. So basically do a big case statement on the type level and write all these cases individually. And actually there's not all that much abstraction in generic programming and reuse between different generic functions. So that's one of the main arguments here. But obviously, that also makes it harder in a way to learn, because these combinators have complicated types and they all work on the type level. And while the definitions are very short in the end, you first have to get familiar with all this. So unless there are questions now, let's perhaps do a second example, which is the mappend. Second one should hopefully get a bit simpler. The type is very similar. So we have exactly the same constraints. Okay. And the type, well, of course, the end type is A to A to A. And now we have like a whole wrapper where we say, well, in the end, we have an A again, so we have to apply 2 in the end, and we have to apply ZOP in the end again. Oh, well, actually, let's perhaps not even go to that level. Let's say we have to apply 2 in the end, and then we work on the representation. And then we want to do something with the from of X and the from of Y, where X and Y are the 2 arguments. So this is the mapping between the original types and the representation, right? And now we just have to take 2 sums of products and merge them into one. And that is essentially a form of zipping, right? But we have to rely on the fact that we have a single constructor again everywhere. So what we are going to do again is, like, the end result is going to be of our single constructor. And here we are going to unpack the 2 things where there are reverse functions. So we're going to do unz of unsop of from X and unz of unsop of from Y. All right. And then we have just, did I put the right number of parentheses? Probably not. No, not nearly enough. Let's see. Yeah, okay. But now it's not. No, I should have put more here. Yeah, so there's 1 missing here. It's Lisp. Okay, this is good. So perhaps. So. And then now we have to glue together 2 n-ary products into one. And I already said it's a bit like a zip width. And indeed, there is a function that is called HCZipWidth, which is much like HCPure. It's a constraint variant of a heterogeneous list zipwidth, where we again have to say we want to do a proxy monoid. And then the only thing that we need to say is how to combine the 2 things. And that's essentially mappend, right? Only that everything is again wrapped in these I constructors. The 2 arguments are wrapped in an I constructor, and the result has to be wrapped in an I constructor. So we actually have to say lambda I A I B to I of mappend AB. Okay, and that type checks. Oh, I'm surprised myself. So if we do, what was the type of LP again? LP was a list of int and a list of bool. So if we take LP of 1, 2, 3, and then of false, and if we mappend that to an LP which just contains a 4 and contains true, true, then we indeed get the one that we expect. Okay. All right. Questions? Okay. So if we wanted to make a monoid instance for list pair, we now can, using gmempty and gmappend, we can do that relatively straightforwardly. Because monoid is already defined in the library somewhere, we unfortunately cannot make it any simpler than that. But if we are giving generic instances for our own classes, we can use a GHC language feature that's called default signatures to actually explain that if there is a generic instance and if these extra constraints are fulfilled, then this is a way to derive a generic definition. And then you can essentially use either empty instance declarations or even with derive any class, but that's still a slightly fragile feature, use a deriving statement for these kinds of classes. And that's it. Okay. All right. I want to show you one more example, and then I'm going to talk a little bit more, but only a little bit about the technical details. I have to defer most of the technical details to either offline discussions or pointing you to papers. Okay, so here's another example which is building on the monoid thing that we've seen. So this is another. It's a small thing, but it's one that I've actually used generic programming for a couple of times. So assume you have a simple enumeration type in your program, and in lack of a better example, I just took a list of room numbers where you might want to schedule talks in. And so you have these 4 rooms, and there is a room data. And this is the typical instance of bounded and also enum, right? And bounded is the class that gives you I'm focusing on bounded now. It gives you a min bound and a max bound element. And min bound, if you derive that, will give you R101, and the max bound will give you R300. And in particular, if you also derive enum, then you can nicely enumerate all these values. But now, I don't know, somebody decides that, oh, room 101 is really much larger than all the others, so they're going to split that room into 2 rooms in your building, and you suddenly have a room 101A and a room 101B. And obviously what you can do is just do this, right? But there is also something to be said for saying, like, room 101 part and let the room 101 part be A or B, because that keeps the relation between the actual physical room it's in and the semantics. Only if you do that, suddenly GHC will start complaining. And why will it complain? It'll say because R101 part is not in scope. That's because it's separated by a Template Haskell declaration. Yeah. And that's why I don't like Template Haskell. Well, one of the reasons. No, it'll say, I'll read that to you. I can't make a derived instance of bounded room. Room must be an enumeration type. And enumeration consists of 1 or more nullary non-GADT constructors, or room must have precisely 1 constructor. So none of these conditions are fulfilled, but it's rather sad, right? I mean, clearly it's both still bounded and enumerable, and just GHC's deriving mechanism is too lazy to work it out. So perhaps we can fix it, and by giving our own generic definition of min bound and max bound instead, that allows us to use this scenario. And so I'll remove the deriving bounded, and I'm going to write gmin bound. And again, this is going to be generic of A. And ultimately, we're going to produce an A. And it's very similar to the empty case, right? We want there to be at least 1 constructor. But in this case, we really want there to be at least one constructor, right? And not exactly one constructor. So how are we going to say that there should be at least one constructor? Well, we say the code of A should be a non-empty type level list. So it should be of the form x cons x's, or let's say, because this is still a list, let's say, so x's cons xs's. And then we want at least, now we can be like, I mean, there are different degrees to which we want at least all the elements in the first list to be bounded, all bounded XS. Right? We could also say all elements everywhere should be bounded. That's possible as well. And there is a function that's called, or a type level function that's called all2, and then we can pass it a list of lists. Right? Actually, I'm going to go for this one because it's slightly easier to implement the max bound with this kind of requirement. Let's see. Again, we're going to do 2 and ZOP and Z and HCPure, and it's basically to say proxy of bounded and I min bound, and that's it, I think. What's this about? Oh, completely unrelated. Okay. So that's giving us the min bound. So let's see, G min bound of type room. I used it. Okay, so that's good. I mean, it's actually saying, oh, there is no instance of bounded R101 part, but R101 part is easy to still make an instance of bounded. We don't have to resort to G min bound for that one because that's still a simple enumeration type. So so now we get R101 of A, which is exactly the one that we want. Now a different way of doing this, of deriving the G min bound, and as I said, this makes it slightly larger, slightly easier to derive the max bound as well, and it also shows how you can do other generic functions that generate like more arbitrary values. Is to use a function that is called app injections POP. Oh. So let's just focus on the last line of the type. It's taking something that's called a product of products. And what's that? That's actually a two-dimensional table, right? That has as many entries as there are constructors in the data type, and for each constructor as many entries as there are fields. So that's a product of products where both the inner list and the outer lists are interpreted as heterogeneous lists. And then it's going to apply the first constructor of the data type to the first row of that two-dimensional table, and the second constructor of the data type to the second row of that table, and the third constructor to the third row, and so on, and the last constructor to the last row. And then it's giving us a normal list back that contains basically yielding from this two-dimensional table elements of that data type and representation form, one of each constructor, right? And then we can then if we are still interested in the first constructor, we can just take the first element out of that list. And if we are interested in the last constructor, we can take the last constructor out of that list. So so let's actually rewrite G min bound using this one. That would look like this. We are going to do app injections POP, and we're still going to use HCPure of proxy bounded of E min bound, and then we're going to take the first element of that list, and then we're going to apply 2 to the first element of that list. And let's verify that that still works. And it gives us the same result. So what are we doing here compared to the upper version? We're calling HCPure at a different type. We're, rather than generating just a single row, just a single list, we're actually generating the entire 2-dimensional table. Right? We're generating a product of products using HCPure, where there is min-bound everywhere. But then ultimately, we're using this app injections POP to get a list of constructors where min-bound is applied recursively everywhere. And then we're taking only the first element out of that, and that gives us the min-bound we're interested in. And correspondingly, max-bound is very simple to write in comparison, because the only thing we have to change is we have to take the last element out of that list and we have to call max-bound recursively. But apart from that, everything else is the same. And then that's giving us R300, which is the last one. Okay. All right. So I'm going to skip the part where I'm going to show how to derive a simple show function and how to get back at information such as constructor names. I just want to say that you can, and actually you can do so in a rather nice way. That's another advantage of this particular approach to generic programming compared to others, that the metadata of a data type, like the names of the constructor, the name of the data type itself, and the names of the record selectors and so on, is available for you, but it's available for you completely independent of the original data type, which is nice because we don't have to worry about it at all if we are not caring about it. For all the functions we've written so far, we didn't need to do any extra complexity because of this metadata. Whereas, for example, in the built-in representation in GHC, the metadata is sprinkled all over the case. I can perhaps show that once just to show you what I'm talking about. If I'm saying, like, for example, if I import GHC generics, and if I say derive generic, and if I say deriving GHC generic of the expression type, deriving instance, sorry, and then I need to enable standalone deriving, sorry. And if I ask for the representation of, that's the GHC representation, not the one that we're using here, of the expression type. This is how it looks. And if you squint a bit, it's all metadata. I mean, that's why it looks so horrible. There is all this stuff about, oh, the constructor is actually called blit, and it's actually a prefix constructor, and oh, there is actually no record selector here, and this sort of stuff. So this is what fills it all up, right? So it's really nice to be able to separate all that noise out and have it elsewhere. But at the same time, it's still very type safe in Generics-sop, because the metadata that you have is also indexed over the code. And so you know that the metadata is compatible, and for example, that you have as many constructor names available as you actually have entries in the outer list of your data types code. So even though they are separate, they are matching up, and the type system can guarantee that you can match them up properly. Okay. So let's let me close by just showing you how these types really look, and give you a little glimpse of how the functions for them look. At least, like, perhaps we can define a map function over n-array products as one example. And there are many of these higher order functions in the library. So the n-array product is essentially a list, right? It has a nil constructor and it has a cons constructor. And the nil constructor does take no arguments. It just produces an n-array product. And the cons constructor takes two arguments, one which is the first element and one which is again an n-array product, which is the tail. So now about the indices. So as I said, an n-array product is parameterized over two things. The second thing, access, is what I typically call the signature, and that's a type level list of things. And I don't care what these things are. So these are kind polymorphic. It's a list of Ks. And the functor that I pass in here takes a K, takes a thing of type K, and interprets it as a type. So in particular, if that functor is I, then you get just a plain heterogeneous list. But another interesting common case is if that functor is K, a constant functor, then you get essentially a homogeneous list, but the number of elements in that list is still statically determined to be compatible with either the number of constructors or the number of fields. So that is isomorphic to sort of a GADT vector-like structure, as you often see. All right, so that's both captured by this NP. Another common case that is useful in practice is if you instantiate F with an applicative functor or a monad, and you basically do an I/O action for every element in your data type, then you get an NP I/O of your things, and then you can apply a kind of sequence operator only lifted to these heterogeneous tuples, where you say, I want to execute all these I/O operations in sequence and get the n-array product of the results back, right? So that's another common case. So that's the n-array product. And how does the n-array sum look? Well, I've already said it's essentially an index into a choice between n different elements. So again, this is indexed by the same things. It's indexed by a list of Ks and an interpretation that takes the Ks to stars. And the first thing to notice is that there is no way to index into an empty list. I mean, if you have a nullary sum, then there simply isn't an inhabitant of the NS type except for undefined, right? I mean, if you have 0 elements to choose from, there is no choice you can make. But if you have at least one element to choose from, then you can pick the first element, which is what the 0 constructor does. So if you inject an f of x, then basically it gives you an access, or like, I mean, taking the pattern matching perspective, if you pattern match on a z, it gives you access to the f of x, which is the first element in the n-array sum if the list starts with an x, right? Or we decide to disregard the first element, and then we still have to choose from the remaining elements. And that also requires there to be at least one element, right? And obviously, if we have only one element, a single element, then the successor constructor is non-inhabited, because we then have to produce, again, a choice between 0 elements, right? So it's really the case that for a 1-element list, we have just one choice, and for a 2-element list, we have just 2 choices. It's perhaps enlightening to look at the type of 0, which really say I can inject an a of x into an n-array sums of a of x cons xs. And if I have successor after x, I can inject an a of x into the second position of an n-array sum that contains at least 2 elements. And if I do successor after a successor of z, I can inject an a of x in the third position of an n-array sum contains at least 3 elements, and so on and so forth. Right? So, so that's that. Can I still talk for 5 minutes? Is that okay? And then is that? Yeah. Okay. Okay. So here are 3 examples of n-array products, just to get like slightly more familiar with these. I mean, the first one is an n-array product of identity things indexed by an int char bool. So it contains an int followed by a character followed by a bool. The second is an n-array product of constants, again indexed by the same list, but it contains an integer for each position. So, but it has to contain exactly 3 elements. And the third one is is parameterized by maybe. So it contains a maybe int followed by a maybe character followed by a maybe bool. Okay, so these are interesting things. So let's not do the hcollapse, but let's do the hmap. As in order to show one function that one can usefully define on such n-array products and also similar such data structures. So if we want to define hmap, the first big question is, like, we want to do a map over a heterogeneous list. It's already unclear what the type even should be, right? I mean, what kind of function do we want to map over it, and how should it look like? And obviously, it has to be a relatively polymorphic function, because we don't know what types we'll encounter, right? I mean, just in the example, there is an integer and a character and a bool, so we have to have a function that is able to somehow deal with them all. And it turns out that this is one of the reasons why we parameterize over the functor in the first place, that it's useful not to worry about changing the signature at all, but rather about changing the functor. So the hmap function over these products will take an npf of access to an npg of access, and will leave the access alone. So it never changes the signature, it never changes the length, but it can change the functor. So it can, in particular, map np of i's to another np of i's, which is a function that may change every individual thing, but it doesn't change any of the types, right? It can also map an np of I to an np of k's, which means it maps all the different types to the same target type. It can, in theory, also do the other way around, like go from a common seed values to all sorts of different types, from k to I, and so on and so forth. And in the simple setting, what we need in order to do that is we need a function that for all element types x goes from fx to gx. So that is a rather strong requirement, but it's certainly enough. So if we have something that independent of the element type always takes an fx to a gx, then we can implement it. And that's not the most useful version of the function, but that is at least really simple to define, because the code, despite all the scary types, is exactly how map should look. Right? So yeah, okay, it warns me that the f is unused, so let's put an underscore there. Right? Okay, but so the code is just map, right? I mean, that's just map on a list. It just has a much more fancy type. Okay, so that's an example, and there are like somewhat useful things we can do. We can, for example, take the example1 list. Let's load talk 2. We can take the example1 list and hmap just over it. Not quite, because the original list is wrapped in these I constructors, so we have to un-I all the things and then apply just to them. So now we just after un-I is indeed a function that has a sufficiently polymorphic type. For all A takes an I of A to a maybe of A, right? And that works, right? We can do it. But the more interesting case is HCMap, which takes a constraint function where we have a thing to map over that has a class constraint, and then we can do something like, if we require that the original n-array product, that every element is in the show class, we can call the show method on everything, and then we get a string for, and then we can turn an NP of i's into an NP of k strings by applying show to every element in the n-array product, and that's a typical useful application of this function, and so it also takes an NPF to an NPG access, but here we need to do more things because first of all, as I told you before, GHC isn't clever enough to figure out what the C is by type inference. So we have to use a proxy in order to tell that to GHC explicitly. That's what we've seen in the example calls. And also, we need that all the access are instances of the C class. So we need this kind of all C access constraint. Okay. I'm almost there. All, despite appearance, is actually rather simple to define. All is just a type family that takes a k to constraint and an access, which is a list of k's, to a constraint, where all of C of the empty list. So if you have no elements in your list, there is nothing to require. And that is a way to write the empty constraint in Haskell, or in GHC, I should say. None of this is Haskell. This is all GHC. Right? And then if you have a non-empty list, then we want that C of X holds and that all C of XS holds. Right? So it's not actually that horrible. And then actually the code is almost the same again, so I can even start copying it. I just have to take the proxy argument and pass that on here. But the rest is still, it still looks like a map should look, right? Okay, and then, I mean, you have zip widths and pures, and you have a number of other functions for n-array sums. But this is essentially, these are the techniques that play a role in there. You have these rank n types where you take polymorphic functions. You have type families, but they're mostly just used for these constraint combinators. You need, unfortunately, that's not really a good thing. You need, unfortunately, these proxies for the constraints because the type inference isn't good enough. And what else? I think that's essentially it. I mean, those are the main ingredients, right? And but that's the library, and you can write arbitrary generic functions with it. And if you want to know more, talk to me offline. There is also some summer school lecture notes that I used at a summer school in Oxford that are much more detailed, that have something like 25 or 30 pages of material, which does this all in a bit more detail. And then let me conclude with an advertisement, and thank you.
You're nesting a lot of constructors, so you're jumping around a lot on the heap. How does performance look like of these things? If I imagine you do the same thing with Template Haskell, you can kind of generate things that are optimized for that.
So the question is, what about performance? And it's a very valid question to which I have no answer, essentially, in the sense that I haven't even tested how horrible it is. I have used this library in practice in situations where simply performance isn't critical, and it's quite convenient to use. And there has been significant performance testing for generic programming these days, but not for this library. So, so the general thing is that in some situations, the GHC inliner is actually rather clever and can optimize quite many things away. But I think we have to be fair to say that in general, this is still relatively fragile. And if you really, really, really want to squeeze the best performance out of it, then using Template Haskell at some stage of the process seems unavoidable. But there are interesting hybrid approaches. Like, I mean, for scrap your boilerplate, there are these, there is GenIPlate and another related approach, which is called Template your boilerplate, which basically gives you SYB-like combinators in order to more conveniently construct Template Haskell programs. And in principle, something similar might be possible for such an approach as well. And a different technique would be just to give you, as a programmer, more and also more reliable control, perhaps, over the GHC inliner, because there are certain recursive functions that are involved in places here that I would really like evaluated statically. And I'm willing to basically, as a library writer, to take the responsibility for the fact that they should always terminate, because they are only invoked on sort of for example, on a conversion of one data type into another, and the data type, the representation of a data type itself is always finite because there can be only finitely many constructors and so on. So if you could sort of have a feature where you could annotate certain functions as being evaluated statically, then one might get sort of more reliable performance out of these kinds of things as well. But right now, I think you have to be careful. Like, I mean, there is a certain overhead involved. It depends on what you're using these things for in the end. I mean, very many applications of these sorts of things are not performance critical at all. But if they are, yeah, I mean, there's certainly an overhead involved, and you have to be aware of that. It's the main reason, by the way, why we still in GHC, despite having like generic programming mechanisms in GHC for a while the deriving, EQ, and ORD and bounded and enum are still implemented in an ad hoc fashion in addition to the generic mechanism, because we cannot guarantee that the generic versions are always going to be equally performant.
One more last question.
Okay. The question is not directly related to Generics-sop, but I'm interested if there are developments in generic programming with GADTs. I guess it can be more approachable after the GHC8 with type and type.
So the question, if I understand it correctly, is whether there are generic programming approaches that can represent GADTs.
Yeah, exactly.
Exactly. So this is something that I have glossed over in this talk. And which data types are representable. I mean, I've just shown you write the template Haskell invocation derived generic on your data type, and then it always works. But in fact, no, it doesn't. So there are certain constraints. And one major constraint is that derived generic does not work for GADTs, and that's the same for the built-in generic mechanism. So yes, indeed, type and type changes the game a bit, and also other things change it. I mean, from already a long time ago. The question is actually not that much like how to represent GADTs at all, because that is doable, but how to make the resulting library a library that is not too horrible to use. So you can see already here, like, I mean, I guess if you ask different people in the room, I would guess you get the full range from this is really cool to, oh, this is horrible, I would never touch it. I mean, even for me, there is a point that can be reached where I think I don't want to impose that on users ever, and where you have to basically like add proxy arguments where the type annotations are longer than the entire generic function that you that you want to write and things like that. So. But this is something, yeah, I mean, there are some papers on how to represent GADTs in a few cases. So José Pedro Magalhães has written a paper on this a while ago. But I'm also currently investigating new approaches for encoding data types made possible by type and type that will enable you to represent a much larger class of data types. So there is hopefully more to come in the future in that direction, but it's not there yet. Okay.